We are joined by Professor Ajay Sood, Principal Scientific Advisor to the Government of India, for a special conversation. Joining him is Michael Nensel, Senior Fellow, Technology and International Affairs Program, Carnegie Endowment for International Peace.
Well, welcome to the most difficult session of the day. It's the most difficult because we're dealing with one of the hardest to understand topics, one of the most futuristic topics, and we have exactly 30 minutes to explain it all and what the impact will be in 5 years, 10 years, 20 years, and 30 years. Luckily, as was mentioned, we have the Principal Science Advisor to the Government of India to help explain this. And I think we have just enough time to provide you with a few insights on what India is doing with its quantum mission and what we're going to be able to realize because of that. I'm particularly glad to be doing this because I've been with Carnegie for 3 years, and it's the first time I actually got to come in person to the Carnegie Global Technology Summit. I've usually been up at 2 o'clock in the morning in Washington, D.C., participating remotely. But I'm also very glad because when I was in graduate school, my housemate was Peter Shor. Peter Shor, if you don't know, created Shor's algorithm, which was the mathematics required to do something useful with quantum computing. And that was more than 30 years ago. So I've been watching the development and getting more and more excited as quantum computing and quantum communications and quantum modeling become a reality. So we're here to just go through the different aspects of quantum technology and applications, and then understand why we should be even more excited than we already are about this. So I'll start by asking the obvious question. You have a portfolio that's huge. You get to advise the Prime Minister and the key officials on everything from biology to graphene to social science. Why are we here talking about this particular topic, and why are you personally excited about quantum technology?
Good. First of all, let me thank all of you to be here and Carnegie Summit to have me here. Now, why quantum is because that's the topic given to me by Carnegie, this thing. But honestly, if you look at what our office does, we have two arms. One is called Science, Technology, Innovation Advisory Council to the Prime Minister. Another one is Empowered Technology Group, ETG. So these two verticals have different roles. So under PM Strike, I was a member when I made a presentation to our Honorable Prime Minister on quantum technology. That was about 2.5, 3 years back. So that time itself, we had debated in our PM strike that this is a technology India must do as a mission mode. Some work was going on in fragmented manner, but we realized it cannot be done like that. If we have to be relevant, we have to do it in the mission mode. So I am glad that it started with that after some time, and then the COVID took its toll to delay the things. But good news is that it has almost happened, and the mission will be formally launched very soon. So that is the way PSA office, my predecessor, Professor Vijay Raghavan, had this PM strike discussion, and it so happens that I am here to take it forward. So that's just a coincidence, I guess, a good coincidence.
Well, the fact that you made that presentation, I think, is why we're here. But the fact is, this is not a small initiative. This is over $1 billion over the next 5 years, and it's not just about quantum computing. It's also, as I said, quantum communications, modeling. Can you talk a little bit about the stuff we never hear about?
Yeah.
The journalists typically write 400 words, and it says quantum computing is totally different. It allows us to do more sophisticated computing for certain kinds of problems like encryption, and then it doesn't talk
Yeah.
about all the other stuff that we should
so
be excited
I'm glad.
about.
So let me take you to this quantum mission, what it is going to be very soon. So we have 4 verticals: quantum computing, which you said, quantum communication, quantum sensors and metrology, and quantum materials and devices. So these are 4 verticals. Each vertical, of course, has many horizontals. So in quantum computing, as you said, there are many things, and I have not met anyone who has been so close to Peter Shaw as you. So you actually are more expert than anyone in the hall by induction. So you have directly.
You're assuming I understood what he was saying to me 30
but that's a
years
good
ago.
news that, but you were there at the right time. But jokes aside, what I'm saying is that all these 4 verticals are important. Now, quantum communication is already something which has moved quite ahead. And it will be the first thing which will be in public domain as a service before the other 3 technologies or 3 verticals take over. So we already have in our country alone, we have 150 kilometer transmission in using QKD. As all of you know, that what we are talking is that the message is sent classically, but the key is quantum. That's why it's called quantum key distribution. So you have to save the key and not work on the message. And this is already done, for example, using entangled photons and using the qubits. And that has already been done in many, many countries. People have gone to now 2,000 kilometers of communication and now satellite link communication. But the key technology which is yet missing around the world is the quantum repeaters. So what happens if you are using entangled photon, every 200 kilometers you will need to boost the signal. That is what is done in our fiber network which we are using. Now, if it is quantum way of doing, you cannot do this automatically because you have to first decrypt, remove the quantum key, then enhance the signal, and then encrypt again. Decrypt, encrypt, this combination goes on every 100, 150 kilometer depending on your fiber. Now this is a big challenge because at the time when you are doing decrypt, that's where you will be attacked. And people who are attacking you are smarter than you and me. So that's where this is the weak link. So the quantum repeaters is the need of the hour. And that has to happen sooner than later. Once we have quantum repeaters, which means the safe transmission over a very large distance, we can say that we have reached there. But even without that, even with this normal way of doing classically crypting and decrypting, it will happen soon, sooner than later. Quantum computing is something where there is a lot of hype. Mm-hmm. So I thought we should talk about it because we should also know the reality. So the big hope is, which is I'm sure it will happen in our lifetime, what you call quantum supremacy. What it means is the problems which cannot be done by classical computers can only be done by quantum computers. For example, the problems of optimization, complexity, for example, traveling salesman problem, which is really exponential in complexity, that's where quantum computer will come in. For practical application immediately, if you can envisage how to decipher all the quantum states of a molecule, you know the pathways then. For example, photosynthesis, you know it's the most efficient process nature has. Mm-hmm. But we still do not understand how it is so efficient. But to have a quantum computer to look at all the quantum states of a photosynthetic molecule and its process is way, way away. Recently, in 2 months back, there was a paper which said that what is bothering us, bothering the whole thing, is the noise which is generated in the quantum gates, because you need gates to do the processing. After 170 gates, you have the noise build up that it loses its accuracy. This is where you have to work on. So even for 8 atom molecule, it is a challenge. Photosynthesis will come much later. So we have to be patient in our understanding and contiguous funding. This is where we need the support of the government, because the private sectors will of course come in, but it is a long haul. So quantum computing, and there is another thing which we should worry. There is no convergence on which technology in quantum computing will take over. There are 4 or 5 competitors. Everyone is looking at superconducting Josephson junction. For example, that's what Google published few years back. IBM is doing it, and many other 2-3 more players are doing. But that is only one technology. Is that the end of it? We don't think so. So I am just saying this is yet to be evolving. We are really, what we were in classical computers in 1960s, when few people had some luxury of doing it and they were doing it. But we are at the same stage now. But the good news is the progress is very exponential now, unlike those times. Mm-hmm. So we will see the results sooner than later.
So let's talk about the sensor side of this. And again, this is something that has been around for a while, so it's not quite as new and as exciting. But I actually used SQUIDs, which are superconducting quantum interference devices to measure very low magnetic fields for my PhD thesis, and that was 30 years ago. What's the next generation of quantum sensors going to do for us? Is there something there that we can explain to a journalist or a congressman in 30 seconds that will get them excited?
Yeah, so I will attempt. It may be 60 seconds. The point is that SQUIDs are known to look at the low magnetic field, but their practical application, for example, in MRI devices, is still to take place. MRI is the one which all of us would come across, either for us or for our relatives. But it is still a huge machine with the sensors which are not so sensitive. A lot of work is going on. So immediately $1 billion industry is waiting for MRIs to be equipped with these quantum sensors. Huge, huge potential. And I'm sure it will happen before anything happens. Then you can also have a very exciting application to measure the change in the gravitational attraction of Earth from your place to my place. We know gravitational constant. In our textbook, we read some number. That number is not sacrosanct. That number, the G is there, but the attraction, the force, depends on the mass of the Earth, which is nearby, below us. So if you can detect the change in that gravitational acceleration, you will have a huge potential. For example, can that be used to see where the oil wells are? Can that be used that enemy has a tunnel running below? Can you have a use that some water body is hidden? For example, in India, we are very fond of asking whether Saraswati River, what happened to that? It is now underground. There can be debates. I'm sure previous session might have some overlap, what I heard in last 2 minutes. But I'm just saying these questions can be addressed in a non-invasive manner if we have quantum sensors. So my sense is the era of quantum sensors is there, But you have to really find a niche to use it.
Well, this is quite coincidental because in 1985 I came to India for the first time to do my field research, and I was measuring gravity about 100 miles north of here without superconducting quantum devices.
Yes.
So looking forward to being able to do that 100
Yeah.
or 1,000 times
Yes.
better, and being able to see, microscopic movements in the earth
Yeah.
is the kind of unexpected thing that we could see with quantum devices. That's for me, that's the exciting thing. As a futurist, I'm always looking for
Absolutely,
the
absolutely.
surprising joker that comes out of the deck of cards, the combinations that people didn't think of.
Yeah, actually, our imagination can take any shape. Even when we are doing quantum communication through entangled photons, and if you think it is not going the way you thought it is going, actually, that information can be used because that information is going to be specific to that place. So you can really think like that. A disruption can actually be used to your advantage.
So how do you do this? You spent most of your career as a research scientist. You've written more than 300 research papers. You're now a
No,
policy
450.
450. Okay.
And still going.
That's impressive given all the other responsibilities you have right now. But you're a policymaker, but you're also a salesman. You're trying to convince the parliament and the other members of the administration that this is worth the money. And this is $1 billion, and it's something that might be like a lottery ticket. It may not work. So how do you make that sales pitch?
Yeah.
How do you convince somebody? It's a little bit like cold fusion.
Yeah.
It might be 5 years
I
in the
hope
future.
it's not cold fusion.
Well, let's ask
So
about
let's
that.
take it. I think we are talking of totally different things. Cold fusion, some people still die for it. I'm not, because if somebody is
Well,
in the
not,
hall,
not cold fusion.
believes
How
in
about
it,
how about hot fusion? Hot fusion has always been 10 years away as well.
But I'm saying that actually what I have found in my limited stay in this job for last 6 months now, actually if you are very honest in your evaluation and not hyping it, it works the best. So when I am asked to give advice, I really take it like a research problem. So I do all the homework along with our team and look at pros and cons of that and present that to the leadership. And also give the opinion what this could be a better way. And I have found that you don't have to hype, actually.
And they can deal with the uncertainty. They can deal with
Yes.
the fact that this might
Yes,
be a 1 in
because-
10 chance.
Yes,
Yeah.
yes.
That's much better than in Washington, D.C., I have to say.
No, I think you have to do that because otherwise you will be going a path, in the end you will be disappointed. So we don't want to have that too often, but we will try our best to make sure that what we promise is delivered to a good extent.
And delivery means not just a research paper, it means applications. And your official title for this is
Yeah.
Quantum Technologies and Applications. How do we convert these
So-
discoveries into
Yeah.
applications and startups
Yeah.
and jobs and revenue?
Michael, very good question. So what we are now, so this mission, which is about to be launched, is interministerial. It has many departments who are participating, but it will be led by Department of Science and Technology. Now, the model which is being now worked around, that it will be led in clusters or hubs. So there will be 4 hubs for 4 verticals. Under each hub, you will have spokes, which means that the hubs will not be in DST. Hubs will be in 4 different institutes, which will be selected on open competition. That hub is not only responsible for the work in their lab, institute, but in the country as a whole. So it's a big responsibility. And in that framework, startups are integral part of that. So what we are saying in our mission document, that it will not be in isolation. First you do R&D, publish papers, and then hunt for startups. No. So we are saying this time, you take these people along. 20 startups are already there in the quantum domain in India. Not a large number, but we hope it will increase. And we are taking them along with this in the hub model. Now, government will not do that. The responsibility of hub will be to attract the startups.
And to provide the training for some of the
Yes.
people who
Yeah.
will then move out of the university or
Yes.
out of the laboratory
Yeah.
into the startup. And that I think is perhaps the biggest challenge here, because we're
Yes.
not quite sure what we need
No.
to train people to do.
Absolutely.
Because we don't know if the quantum sensors is the most
Yeah.
exciting or the quantum computing.
Yeah.
How do you think through that?
So
how do you place enough bets that you're going to win here?
No, what you're saying is absolutely of critical essence here. I take an example of IT industry. When we started in India, we became very relevant in my own lifetime at the time when this Y2K problem came up. Because everyone wanted to solve Y2K problem, and India had the ready manpower, or sorry, human resource, I should not say. Sorry, habits die hard. So we did not have to wait for human resource to build up. That way, we have to build the human capacity in quantum this thing. But point is, it is not a technology you can pick up in 1 week. There cannot be crash courses. So you have to be patient and bring the whole generation in this. So right from the early college days, it has to be sensitized. Quantum mechanics, the way I studied, and I'm sure some of you would have studied, is done in a very theoretical manner. First you do superposition, you do Schrodinger equation, blah, blah, and you go on. That may not be the right teaching now. You have to now connect quantum to the quantum frontiers. See, the point which you have to realize, I hope I am not putting it in a wrong way, quantum is not new. Quantum revolution already happened in 1913 when all the hydrogen spectral lines were explained. If you did not have quantum mechanics, you could not have understood hydrogen spectral lines. As simple as that. But at that time, we did not know how to control the states of a molecule, quantum states of a molecule. We did not know how to control the transistor at an atomic level. We understood the function of a transistor using quantum mechanics, using Schrodinger equation. Second revolution which you and I are talking is to control the quantum system. So from understanding and usefulness or a transactional value, now we have come to really manipulating the quantum. So that transition is happening now, and that will definitely need our training of the people.
I was fortunate enough to go to Caltech as an undergraduate, and when Richard Feynman was there, and he gave this famous lecture
Exactly.
on how to do quantum computing
Yes.
and how to model the world.
Yes,
And he made this point, which is the universe is quantum.
exactly.
You'd better use quantum models to understand the universe.
Yeah.
And he laid out a lot of the key things we're doing now
Yeah.
because we finally have those instruments.
Yeah.
Let me go back to communications. We have 7 minutes left, and I would like to get a few questions from Twitter or from the audience. One last question on communication. It's been said that it's not what people don't know, it's what people know for certain that isn't true. So what do people know about quantum that's not true? What misperception or myth, particularly among politicians and journalists, would you correct?
Okay. All right, it's a tall question. I think there is a feeling that whatever encryption we are doing now, let's say 128-bit or 256, and if the quantum comes tomorrow, it will be done. I'm saying it will be done, but it will take time. It's not that it is going to happen in few weeks or something, but it will happen. On encryption, I am sure there is a lot of expectation, which will be realistically taking some more time before it comes in our public domain. Quantum computing, which has a lot of hype right now, we are still struggling with the noise at the quantum gates level and the readouts. People have to be patient to take that into view. So people think that, oh, all problems of complicated systems will be solved. I would say it's happening, but even in 2022, we are still struggling with the noise levels.
I would say the other myth I think we already addressed, which is that it's not just about encryption. Because you can explain that part of the problem, often the journalists focus on that, but there's a lot of other interesting problems.
Yes.
You can't solve all problems.
You can't solve.
But there's a lot of very impressive things that are going to happen. So I'd like to turn to the audience. We have 5 minutes. If there's any questions, I think I see somebody coming to the microphone. And if you could identify yourself as well. Please.
Hello? Yeah. My name is Rijul Sachdev. I'm a GTS Young Ambassador from IIIT Bangalore. Sir, I had some questions about quantum sensors. So back in my postgraduate days, when I studied quantum computing, we learned how you can generate truly random numbers using qubits, right? So that's one of the easiest things you can do in quantum computing, which is very hard in traditional computing. You use a whole lot of structures. Doesn't help. But in quantum sensors, like you said, the noise is the major problem, right? And in the case of non-linear dynamic systems, or chaotic systems as they're called, how would they be modeled using quantum computing, according to you?
Can we take the second question as well, and then we'll let him answer?
Thank you. Harry Rolfe here, Australia National University. I'm with the Centre for Tech Policy Design. Fascinating taking a part of the quantum challenge here. I'm very curious to ask a question of you about the geopolitics of this particular technology. In Australia, there's a huge interest in quantum technology. There's a new advisory council that's been set up and some recent breakthroughs, particularly to do with turning quantum mechanics into a chip that you can actually then commercialize and put into a computer in a conventional way. I'm very interested, though, in how, with a mission as India is pursuing and putting so many resources behind it, and how other countries are also doing the same thing, scientific cooperation comes into this. And I'd just be interested in asking you where you see cooperation in the development of this technology and how it can be continuing while countries are competing for quantum supremacy and while this particular technology has such significance for national security.
Thank you. Thank you so much for asking that question, because that's the question I didn't get to answer. So why don't you start with that? Who should India be collaborating with, and in what ways?
This is obviously a no-brainer for me to say that international collaboration is a must in this field, because it's not that some people have achieved not the quantum supremacy, the supremacy, and others are struggling. Actually, the difference is not that large. Some are ahead, obviously, because they started early. Others are catching up. And major economies are putting a lot of resources in this. My sense is the way I have seen in the last 5-6 months of my stay here, almost all the delegations I have interacted with, quantum frontier is on everyone's agenda. Be it US, be it UK, be it Australia, be it Japan, and European countries. So everyone has this agenda. So my own sense is that people are keen, because it has not yet reached a commercial angle that all the secrecy will start coming. It has not yet happened, fortunately. So once that comes in, discussion will become little more complicated. But right now, people are still struggling to put their money on some technology. Like Australia, you said, they are way ahead in phosphorus in silicon chip. They can put individual phosphorus in an organized manner in a silicon crystal, and the quantum states of phosphorus are used as qubit. Now that has come to, let's say, 5 qubits or 7 qubits, but you have to go a long way. You have to go to at least, if you want to solve a reasonable problem, 50 qubits minimum and more. So other countries are looking at ion traps, atomic traps, and make them more easily available rather than complicated lasers and so on. That is another technology which is being developed. So answering that question, international collaboration, yes, it's a must. Coming to the first question, I forgot now.
It's about noise and whether you are optimistic that we'll be able to tackle this noise problem.
Oh, yeah.
And whether there's a way to model the noise.
Yeah, and nonlinear. Actually, the chaos is a complicated problem, as you know. But the point is whether you will be able to model chaotic dynamics and what quantum will bring, I'm not clear. Because classical computation have gone up to a point. But supposing you say, I want to solve 3-dimensional Navier-Stokes problem. 3-dimensional, not 2-dimension, 3-dimension. And in real time, you want to solve some problem in climate change, for example, prediction, or in some wind tunnels or so on. It is enormously computational extensive. That's where if quantum computation can help, it will be a game changer. So that is one, and I'm sure it will happen sooner than later, maybe over, I don't think it is good to give numbers because then you are stuck with that number, but let's call it few years. That's one area. So that's where you see turbulence, you see all that. Classically, turbulence is understood up to a certain point. You understand the power spectrum, you know what is the spectral function. But if you want to go deeper than that and want to control turbulence, that's where you need more insight, and this is where quantum computing could be of essence.
So we've run out of time, but I always like to ask the last question, and it's very simple. What's the one-sentence tweet that you would want everybody to tweet after hearing this talk? And for me, the tweet is, it's even more exciting than you thought, for reasons we don't know, and you'll have to be patient. So what's your tweet?
Last one, you took my word.
Oh, okay.
I would say, quantum is here to stay. Don't wish it away. Invest energy, time, and money, and be patient.
And $1 billion over the next 5 years.
Everything,
Okay.
yeah.
Thank you very much. Very, very.